Much for logging in this morning and being with us this morning. Thank you very, very much. I must appreciate the fact that there are a number of seniors, professors who are always with us this morning. And I can see a number of them have not come yet, but I'm sure they will be in. But I want to appreciate very much our professor, Professor Joseph Mutai, for giving us the opportunity, a platform like this that we'll be using to share ideas every Sunday morning. We must appreciate you, Professor. Thank you very much for the love you have for the students, but also to ensure that we continue learning and becoming better people in this journey. Thank you very much. I must also appreciate you, my colleagues, for logging in. I must say that there are a number of you who have consistently been part of the morning session, the students' session. I want to say thank you very much to many of you. I see Thomas Wabwire from, I think, Busitema. Thank you very much, Thomas. I see Samuel. Samuel, thank you very much for consistently being part of the Students' Congress. Peace, my sister, Peace, thank you very much. I have noticed that for almost 2 years now, you have been consistently attending. I see my other brother from, I think, Busitema, Mr. Mario Uma, thank you very much. And many of you, I see Monica, and all those who are new, I see Hosea from, I think, Zimbabwe or somewhere, I think. Thank you very much. This is an international platform. We have students from different parts of the world coming in and being part of the session. So thank you, and thank you very much. I am sure if you did not log in, I would have no business this morning. I would have nobody to speak to, but because you have decided to come in, thank you, and thank you very much. Your efforts are really appreciated. I usually and consistently remind ourselves that we have a big task. We have a lot. This journey that we have embarked on is very rigorous, very tiring, it's very draining, but we have chosen to walk through the journey. There are a lot of thorns, there are a lot of potholes, but nevertheless, you'll find at one point you're clashing with your colleagues, you're clashing with your family, at some point you are not agreeing with your supervisors, but that's the journey. We just have to find a way to manage it and move on. So thank you, and thank you very, very much. Now, again, as I've always mentioned, we find ourselves joining the PhD journey at different levels. There are some of us who have been in this journey for the last 2 or 3 years, and you have moved. Probably you are now handling data collection. Some of us have just joined and you're still trying to craft the topic. Others are in the middle there. So we are at different stages. But what I think is critical is for us to learn to share ideas together. That is one. But also two, you might find that some of the content that we share in the morning, first hour, could be something that you have already gone past. But for the sake of those who have just joined, I just want to encourage that for those who have gone beyond that stage, you should be able to contribute, because usually after a clip, I always give some few minutes for us to discuss. So that's a better time for you to come up and share with us your experience. How have you managed to move that far. And if there is anything really that you can share, that's the time. So today, again, I want us to just go back a bit and refresh our minds. We've been handling data for some time, but I thought that maybe today I want us to again go back and look at theory in the context of reality and knowledge. Theory in the context of reality and knowledge. And so I want to invite us to watch some of the works of our very own Professor Joseph Mtai. I want us to watch his particular lecture on theory, and some of the things that he puts concentration on in this particular lecture is the issue of the actual reality, the issue of knowledge, and the issue of presumed reality. So these are some of the things that he is going to discuss in this clip that we are going to watch and listen. So allow me now switch my gadgets here so that I can be able to share with you this clip or this lecture. Then in the end, we'll be able to give our response in terms of our takeaways this morning. So welcome with me to this lecture this morning.
Good morning, ladies and gentlemen. Welcome to our lecture series in scholarly writing for publication. I want to welcome you in a special way to our lecture 6, and lecture 6 will focus on theory in a broader context of reality, knowledge, science, and
I just want to confirm whether you can hear and view my screen.
You can.
Thank you.
research. And if you remember, in our lecture 5, we did discuss issues that relate to theory building, and it was an introductory part of theory building. And we had to do that because we know very well that research involves theory building and theory testing, ladies and gentlemen. And theory testing, the empirical part, while theory building involves the development of models from a particular context or reality out there, and then come up with the propositions, conjectures, or hypotheses that are testable, and so that conclusions can be made at the end of the day. So the results can actually lead to extensions or revisions of those particular theories. But I did tell you that in these lectures we are dealing with the theory building for hypothesis specification, ladies and gentlemen. So lecture 6 is theory in the broader context of reality, knowledge, science, and research. And in this lecture, ladies and gentlemen, I'll be covering two major aspects, and then thereafter summarize. So we're going to look at theory in the context of reality and knowledge. So I'll be talking about actual reality, I'll be talking about knowledge, and I'll be talking about presumed reality. And those are aspects that we even covered in the previous lectures. Ladies and gentlemen, the second part that I'll be covering in this lecture will be related to theory in the context of science and research. And in this particular sense, we'll be looking at science and theory, we'll be looking at research and theory, and we'll be looking at paradigms, actual reality and theory, ladies and gentlemen. And thereafter, ladies and gentlemen, we shall come to the summary, and that will be the end. So allow me to begin, ladies and gentlemen, our lecture, and I hope you are seated and you are enjoying possibly balancing a cup of coffee and possibly your pen and notes, and we are going to exchange ideas that relate to theory building. So let's look at the theory in the context of reality and knowledge. As I have already said, science aims at generating knowledge, and research in a particular form of process is very important. So research in this case is a particular form of process of generating knowledge. And it is a process that is consistent with the features of science as a mode of developing knowledge. And research can be seen as consisting of two parts, ladies and gentlemen, as we have already seen. And the first part is theory building or conceptual research, where conjectures about reality are generated. And the second part is theory testing or empirical research, where the conjectures are subjected to empirical verification. Now, the focus of this lecture is on the first part of these two parts, namely theory building for hypothesis specification, which can be termed as the conceptual part of the research process, which can then serve as the starting point for the subsequent empirical examination part, ladies and gentlemen. And since hypothesis specification is a part of research, and research is an approach to generating knowledge about reality in a manner that is compatible with the features of science, a discussion of certain broader aspects of research becomes relevant. So these broader aspects that we're going to discuss include the nature of reality, includes knowledge, and includes science, ladies and gentlemen. So theory building, as you can see, and development of hypothesis form a part of the research process. And this lecture addresses these broader aspects. And again, I'm going to put back the figure that we had there. I hope you still remember that figure too, so that we really do understand what we are talking about. So if you can look at the screen here, figure 2, because we are continuing with the discussion that relates to that figure. That figure 2 may provide, and it does provide certainly, a helpful framework for viewing these broader aspects that we are discussing in a larger framework, ladies and gentlemen. So as you can see, figure 2 represents a perspective of research, and that's why you have actual reality and the term actual reality, and that's where we started. In figure 2 refers to the phenomenon in the real world that the research seeks to understand, and the term actual reality is used here to refer to some phenomenon in the real world that is sought to be studied in research. So I'm sure you are seeing that diagram too there. And one of the objectives of research is to generate knowledge about reality of the real world. However, theories may be needed as representations of actual reality for various reasons. And of course, direct observations of the real world may be too complex to develop an understanding, or they may not reveal the actual relationships existing between units of interest in the real world. So observations in such a case, although could be used in the data collection process and also trying to model reality out there, but the process might be very complicated or complex. And in such instances, developing a simplified representation of an otherwise complex reality, and, ladies and gentlemen, assessing whether the predictions or conjectures derived from that simplified representation actually correspond with the observations obtained from the empirical world is one of the, it's actually one way of developing an approximate understanding of the real world. And in this process, theory building for hypothesis specification provides conjectures and predictions from simplified representations of the reality, ladies and gentlemen. And of course, once that is done, then we are able to facilitate the process of developing an understanding of that reality. And theories, ladies and gentlemen, are thus simplified representations of the real world. And an example, certainly, that we used earlier on helped us to clarify this issue. And let me just give another example here. In business management studies, for example, some phenomenon of interest may not be observable, or may be observable only indirectly. For instance, if you are dealing with an employee's motivation system that influences his work behavior, this aspect of motivation system is not observable. By the way, even the behaviors of the employees are not observable. And similarly, an employee's values and commitment to the organization and even satisfaction and so on may not be directly observable. So hence, in this case, a researcher may first develop a simplified representation of reality of employees' organizational commitment, and from the picture that come up at the end of the day, may develop a prediction that an employee with a high organizational commitment will form positive behaviors. And subsequently, a researcher may obtain measures of commitment and positive behaviors using various observable indicators for several employees, and would then assess whether there is a very strong relationship, and again I'm talking about a relationship that is statistically significant between those particular constructs that, or the concepts or variables that the researcher is studying, ladies and gentlemen. Now, if this is found, then one relationship in the representation, and I'm talking about theory of employees' organizational commitment, that employees' organizational commitment is possibly related with employee contributions to the organization, is supported. And once that is done, then we have developed a partial knowledge about the reality of the effects of employees' organizational commitment. So in the process, ladies and gentlemen, the process of theory building for hypothesis specification is carried out with an objective of developing an understanding of the actual reality. So let's look at this concept of knowledge. I know it's something that I've been discussing over time, and I told you that knowledge is defined as justified true beliefs. But of course, you remember the Gettier case when we are dealing with the philosopher of science, Gettier, who challenged this kind of thinking. But anyway, without really going into that debate, while the actual reality being studied by researchers exists outside them, they develop knowledge about it. And this raises a question as to what knowledge is and what is its relationship with the actual reality and the theory. If you remember the diagram that we had here in figure 2, that is figure 2, that diagram, it can be put back, so you have actual reality, presumed reality, conjectures, and so forth. So we develop knowledge. Again, we see Kellinger in 1988 provided a description, which is very important, and Kellinger simply says that Kellinger's description indicates that to know is to form beliefs, and thus knowledge can be viewed as a set of beliefs. However, not all beliefs may constitute knowledge, as I've already said. Science seeks to generate beliefs, right, or knowledge that has certain features, and one of the definitions of science, again as cited by Stone, suggests that science seeks to develop a particular kind of knowledge, and that this knowledge is developed in a particular way. It suggests that science seeks to develop objective knowledge, and those are some of the features of science. Objective knowledge that can be supported by empirical data rather than seeking support from individual opinions, ladies and gentlemen. And of course, it further suggests that the empirical data for such support is collected by observing and experimenting in a suitable manner. And that's why you must actually provide a convincing methodology that you went through all the protocols and generate results. Now, this description that I'm giving you of the kind of knowledge sought to be generated by science indicates an emphasis on having an empirical or factual basis of the knowledge. And in the method of science, it is assumed that the objects in the real world, ladies and gentlemen, exist, and whose features exist independent of the opinions that different individuals may have of them. And the knowledge generation in science is done, ladies and gentlemen, in relation to the evidence or objective assessment of the real things. And thus, beliefs are grounded in objective evidence about the objects in the real world or in objective empirical evidence can be regarded as constituting the knowledge that science seeks to generate, ladies and gentlemen. And as you can see in this view, correspondence of beliefs with the empirical world or actual reality qualifies those beliefs to be regarded as scientific knowledge. Let's just take an example. For instance, let us consider a person sitting in a room from where he cannot see what is happening outside the room. Now, that person may hold a belief at the moment that it is raining outside. However, this belief would constitute the person's knowledge or scientific knowledge about the reality only if it is actually raining outside. And therefore, in this example, the correspondence between the belief and the actual reality outside determines whether the belief constitutes knowledge or not. And the correspondence criterion used to assess whether a belief is true or not implies that there may be beliefs that do not constitute knowledge, ladies and gentlemen. For instance, a supervisor may believe that a subordinate is not committed to the organization, whereas the actual reality may be that the subordinate is actually committed to the organization. Now, in this case, the supervisor's belief may constitute misperceptions of the reality rather than knowledge about reality. So, science as a process of generating knowledge can be seen as generating belief statements about the actual world, and we call these conjectures from and about the presumed reality, and then retaining those belief statements that correspond with objectively obtained empirical evidence. So belief statements retained out of this process constitute knowledge in a scientific sense, ladies and gentlemen. And in this view, science generates knowledge as an outcome of empirical testing of the belief statements by retaining empirically validated belief statements as pieces of knowledge. So theory building activity pertains to the specification of presumed reality and conjectures, ladies and gentlemen, conjectures, parts of this knowledge generation process of science. And this activity generates plausible belief statements which are subsequently subjected to empirical verification, ladies and gentlemen. And those belief systems that get empirically supported constitute pieces of knowledge about the actual reality. So this entire process that I'm talking about, generating plausible belief statements, empirically verifying them, and retaining those statements that are empirically supported, constitute, ladies and gentlemen, the research process. And in this view, the aspects of theory building or hypothesis specification, research, knowledge, actual reality get interrelated to each other at the end of the day. So let's talk about the presumed reality. Now, while research, ladies and gentlemen, aims at generating knowledge about the actual reality, and the actual reality may not be directly accessible to the researcher, or may be too complex to discern relationships in a researcher. And of course, developing those relationships might be complicated, and therefore, at the end of the day, the researcher may end up forming what we call presumed reality. So in the process of modeling, you form those presumed realities. So from the actual reality to a presumed reality, of course, that's what you model and put on your paper. So that's what it is. So for instance, in this case, a researcher can develop a conceptual model or theory of what an employee's commitment to an organization is, what causes it, and what outcomes it has. Now, the researcher can specify or reasonably assume, for example, that commitment is an employee's particular type of attitude towards an organization. Then he can make conjectures, ladies and gentlemen, about what organizational aspects cause it. Now, he can also make conjectures about the various consequences of the employee commitment to an organization, ladies and gentlemen. And of course, this becomes very important because at the end of the day, we must go through this kind of process, right? And I think that's a good example that I've just given you, but we know very well what conjectures are, and conjectures are just tentative beliefs, and after developing them, a researcher collects data about the actual reality and assesses whether the data actually corresponds with the conjectures. Now, if it does, then the conjectures are accepted as reflecting the reality out there. And of course, each conclusion of correspondence between the conjecture and the actual reality provides an empirical fact, as I've already said, in the form of an empirically supported conjecture about the reality, ladies and gentlemen. Now, this adds one piece of knowledge to the existing reality. Now, this also strengthens the research community's confidence in the adequacy of the presumed reality in representing the actual reality. Now, this discussion suggests that presumed reality includes a set of conjectures about the actual reality. I'm sure you still see figure 2 there, because everything that I'm describing is actually presented in figure 2, which is still on the screen there. And of course, in the aforementioned discussion, the other aspects of figure 2 also become relevant, ladies and gentlemen. So therefore, some discussions of the components and processes depicted in the figure become relevant at this material time. And we can actually talk about these things. So the first component of the figure is the actual reality. And of course, a researcher seeks to develop an understanding of this. In scientific research, a researcher seeks to develop knowledge about the actual reality. For this, he can develop a plausible view of what actual reality is. And the term presumed reality is used here for the plausible view that a researcher may develop about the actual reality. And this presumed reality may take a form of a theory or a model of that reality. Now, again, since we are talking about modeling the actual reality and presumed reality, I'll ask you, ladies and gentlemen, for a more detailed understanding of modeling reality. I will ask you to go and consult my lectures on the philosophy of science in economics. Lecture 13, which dealt with the models and modeling in economics, part 1. Lecture 14, that handled models and modeling in economics, part 2. Lecture 15, models and modeling in economics, part 3. So you will see how interesting it is. Please make sure that you attend these lectures and make sure that you understand these lectures very well, and then return to the theory building aspects here that takes us into methodology. So what I did discuss in lecture 13, 14, and 15 under philosophy of science in economics, but models and modeling, we're actually helping us to model, come up with the models that represent reality, and in so doing, we were dealing with the conceptual part, which forms what we call theory building. So as you can see, this is very important. Conjectures must be developed, and then at the end of the day, conjectures must be tested, ladies and gentlemen. So again, when you look at that diagram, figure 2, you see the entire research process there. So the researcher then takes out one or more of the conjectures from a theory or model, or the presumed reality, and then that researcher has to specify methods, right, that he can use to collect data relating to those conjectures, and then again the data analytical tools that he's going to use to test those conjectures, because not all of them will be tested, not all of them will be more or less framed in the same way, right, because of the nature of the reality out there. So you may find that you are going to use different analytical tools, ladies and gentlemen. So the issue of research comes in here, right? So we go ahead and obtain data using measurement tools, data collection procedures, and this data constitutes the observed reality. Observed reality is data. Now, of course, you have the other one, which is not really observed. So the observed reality is filtered through the measurement and data collection procedure of the researcher, and thus may not exactly reflect the actual reality. Now, this is acknowledged in figure 2, where the observed reality and the actual reality are depicted as two distinct parts. And then by analyzing the data, the researcher examines whether the pattern of data corresponds with a pattern specified in the conjectures from the presumed reality. And now, if there is a correspondence between the conjectures from the presumed reality and the pattern of the observed data, ladies and gentlemen, then the conjectures can be taken as empirically valid or as supported by the data. And each, right, of these conjectures that is supported by data then provides one more piece of knowledge or empirical fact about the actual reality. And these empirically supported conjectures also add to the support for the presumed reality as an adequate or reasonable representation of the actual reality. So there are several ways, ladies and gentlemen, of doing it. And one of these is to use the existing theories or presumed view of reality as outlined in the previous example that I've just given you for specifying hypotheses for empirical testing. Now, the actual process of theory building, ladies and gentlemen, that can be used for this and the other ways for generating hypotheses will be discussed later on and beyond the scope of this lecture. Now, sometimes, ladies and gentlemen, multiple hypotheses generated for empirical examination may constitute a small theoretical model because the process of specification of these hypotheses also results in the specification of several other units or components of a theory, ladies and gentlemen. So those conjectures from a theory or a model which can be taken up or are taken up for empirical verification, right? And of course, these are called hypotheses, ladies and gentlemen. So hypothesis can be seen as derived from a theory or model that, this is very important because these must be tested anyway at the end of the day. So the process of hypothesis setting may be typically preceded by theory building with an objective of developing testable conjectures or hypotheses. Now, this theory building process for hypothesis setting spans across two of the components that we see in this diagram, which is figure 2, the presumed reality and conjectures in the research process, again depicted in figure 2, ladies and gentlemen. So allow me to move to theory in the context of science and research, right? So why don't we start by looking at science and theory? So Again, as explained earlier, in social sciences, knowledge about actual reality is developed through a long sequence. And the steps in this sequence include developing a view of the actual reality in the form of presumed reality, deriving one or more conjectures from this view of presumed reality, ladies and gentlemen, and carrying out research for verifying whether these conjectures actually correspond with observations made about the actual reality. So, ladies and gentlemen, as you are listening to this lecture, remember, there are two things that I mentioned, and you do not forget these two, because that's why we are having a discussion about theory building. You see, when you start doing research, right, you've got reality out there, and you are seeking for explanations of that particular reality. So you start by modeling, right? And in the modeling process, you look around to see the tools that are available. And those are the theories that scholars have in the past developed to try and explain reality out there. So, and those are the nets, right? And if they can adequately capture reality out there, then you are doing a good job, ladies and gentlemen. But that may not be the case, because reality can be complex, as again represented in the lectures that I've asked you to attend in the philosophy of science, in models and modeling in economics. That's part 1, 2, and 3. That's lecture 13, 14, and 15. That's how you'll understand the complexities of reality. Now, in this process that we undertake, ladies and gentlemen, we know very well that we've got the theory building part, right? And that is what goes through our background or introduction, right, up to the time when we actually develop a model. Right, now you have a second part that we call the theory testing. That's when you come up with the methods, methodologies, and so forth. And then you measures, right, and the tools available to a researcher. You go measure those concepts, collect data, right, analyze data, and then at the end of the day, the results that you get, right, will be compared against the reality that exists out there, the conjectures, propositions, and the hypotheses that you develop from that modeling of reality, ladies and gentlemen. So that's what we actually do, and that's the relationship between research, ladies and gentlemen, and theory building, right? So that's very important. And of course, we know in terms of research and theory, if you look at the definition given by Stone, 1978, Stone suggests that research is examination of a real phenomenon through the adoption of methods outlined or recommended in science. And this definition can be interpreted in light of the earlier cited definitions of science. And of course, I will not really go through all those definitions because you know them, but do not forget that this process is scientific, the process is systematic, the process is objective, right? And you go through that empirical process, ladies and gentlemen. So as a process, right, that adopts methods really which are outlined and documented in the various literature, right, and as recommended in science, and methods again that are in compliance with the guidelines of science, and of course suggesting that research is a process of examining a phenomenon in an objective, systematic, and empirical manner, ladies and gentlemen. So research can be divided into two broad classes, ladies and gentlemen. We've got conceptual research and empirical research, and that's why we started in our lecture 1 and lecture 2 and lecture 3 and lecture 4 when we started looking at issues that relate to scholarly writing for publication, ladies and gentlemen. So you can have a conceptual paper and you can have an empirical paper. So these are actually related. Now when you look at the diagram, figure 2 again, which is presented here on the screen, as you can see, conceptual research focuses on developing the presumed reality and the conjectures, while empirical research focuses on the collection of data and assessment of correspondence between collected data and conjectures. And the theory can be viewed as an outcome of conceptual research, right, and a basis of empirical research that seeks to verify the implications of or even conjectures generated from the theory. And these two parts, as depicted in figure 2 that you see here on the screen, right, interconnected in that they form parts of the knowledge generation process and support each other. So theory and its conjectures coming from the conceptual part of the research guide empirical research, while outcomes of empirical research can suggest the avenue or avenues for alterations in the existing theories, which can then yield fresh conjectures, ladies and gentlemen. And this is consistent with the Durbin 1976, who says that the entire knowledge generation process is actually cyclical. It's a cyclic process containing the parts of a theory and research, and indicates that the process up to proposition specification forms the theory or theoretical part of this cycle. And based on the preceding discussion and in light of Durbin 1976, it can be suggested, ladies and gentlemen, that the term research in the cycle refers to subsequent empirical verification activities, including certainly deriving hypotheses from propositions and collecting data on measurable variables used in the hypothesis, ladies and gentlemen. So, ladies and gentlemen, again, as I have already said, Durbin 1976 notes that these two parts of theory development and theory testing are interrelated and interlinked. And Durbin 1976 again notes that research could take two possible approaches, right, in its task in relation to a theoretical model. It could seek to examine the proof for a theoretical model, or it could seek to improve a theoretical model. And in this sense, research could be seen as closely linked to a theory. And the guiding role of a theory in the research process is also reflected in the works of Kellinger, 1988, I think. So, and looks at the entire scientific research as a process in which a theory and the associated hypothesis about the likely nature of the empirical phenomenon guide the process. And the various discussions suggest that a theory is a significant part of the scientific research process. So you can't actually ignore a theory. You can't ignore theories. So theory building results in the depiction of a view of actual reality in the form of the presumed reality, as you can see in the diagram, and that can be used to provide a set of conjectures about what is likely to be observed in the actual reality, ladies and gentlemen. And these conjectures or implications about the actual reality derived from the theory can serve as the basis for the subsequent empirical research activity. So this is very important that we really think about the theory building and the theory testing part as really major components of research activity. So why don't we then look at paradigms, actual reality and theory? Because when you decide to model reality out there, you have a particular view, you have a particular understanding, you have a particular model, you have a particular paradigm that you are using. So in social sciences, ladies and gentlemen, our understanding of the reality is an interpretation or construction of reality that is distinct from actual reality, and the interpretation or constructed view of reality is influenced by the view of the world or reality that a researcher adopts. And the term paradigm in this case reflects the world view or the alternative view of the reality adopted by researchers. So the term paradigm is used in various ways, right? And if you look at the works of Mackenzie and House, 1978, They suggest that paradigms are a collection of theories, laws, and procedures, instruments of research that are accepted by a number of scientists. And when you look at the works of Morgan suggests the appropriateness of looking at paradigms as worldviews or as alternative realities. And according to Morgan, researchers make certain basic assumptions about the nature of society and the nature of knowledge. And these assumptions, ladies and gentlemen, shape their view of the social world. And the description in Morgan 1982 also suggests, not 82, in 1980, also suggests that under the influence of their worldview, researchers adopt certain metaphors to construct or interpret the reality. So those concepts that you have are actually metaphors, right? And certainly if you relate the metaphors or the concepts, you come up with propositions, ladies and gentlemen. And when you bring them up to the measurable level, then you can come up with hypotheses because you are able to vary. You are supposed to, well, you are able to look at those concepts now as variables, no longer concepts but variables, because they can easily be measured, ladies and gentlemen. So that's what it is, right? So Morgan has that perspective and that view. So as you can see, paradigms are formed by the assumptions about the actual reality and the nature of knowledge, and influencing researchers' construction of the presumed realities can be positioned as an influence on the presumed reality that we have in our figure 2, right? And figure 2 is still on the screen, ladies and gentlemen. So a researcher's construction of presumed reality is likely to reflect, right, partly the actual reality and partly the influence of a paradigm within which the researcher operates. So paradigms can be viewed as reflecting assumptions about reality and shaping the forms of presumed reality constructed in the research process, ladies and gentlemen. And these are important aspects that we need to understand, because there's a link between theories, theory building, theory testing with research, right, and then paradigms, ladies and gentlemen. So whenever you undertake research, the issues of paradigms become very important. And with this, ladies and gentlemen, allow me to come to the end and I give you a summary of what we have looked at. And we meet again in lecture 7, and I will continue with the idea of theory building, ladies and gentlemen. So again, ladies and gentlemen, in summary, in this lecture, we have demonstrated that a theory is part of the scientific research process. And we have also seen that scientific research process seeks to generate knowledge that is objective and based on systematically obtained empirical facts, ladies and gentlemen. We have also come to understand what this process is. And this process involves developing knowledge about actual reality. And these are the things that we do when we are developing knowledge about actual reality. We develop theories of reality. We derive and select conjectures from or implications of theory. We go ahead into collecting relevant data from the actual reality for assessing whether the reality reflected in the obtained data is consistent with the conjectures. Then assessing the correspondence between the conjectures and obtained data is an aspect that we have discussed. And then drawing conclusions as to whether or not the conjectures truly reflect the actual reality. And finally, accepting as empirical facts those conjectures for which there is a correspondence between the conjectures and the data obtained from the actual reality. So again, we have seen in this lecture that these empirical facts constitute scientific knowledge about reality, right? While this process yields an empirical fact about reality, it also yields information about whether the conjectures and the theory from which these conjectures come are valid. So thus the research process generates pieces of knowledge about actual reality by using a theory as a representation of the actual reality, and it also yields conclusions, right, about how valid a representation, a theory, right, or representation of a theory is to the actual reality. And in light of this, ladies and gentlemen, in light of this place of a theory, in the knowledge generation process, a theory occupies a specific place in relation to the actual reality, knowledge, science, and research. So it is, ladies and gentlemen, a constructed view of actual reality, right? An important instrument of scientific knowledge generation, an important link in the research process, an important goal of science, or an important means of facilitating the attainment of goals of science. And ladies and gentlemen, that's what we have covered, right, in this lecture. And a more detailed discussion on what a theory is and its role in the research process will be discussed later, ladies and gentlemen. I want to thank you very much for being attentive. I want to thank you very much for coming. I want to thank you very much for attending these series of lectures during this time. I can always say thank you very much. I wish you the best. Stay well, stay safe. Have a nice time. Bye, ladies and gentlemen.
Yeah, thank you. Thank you very much, ladies and gentlemen. For being part of our students' conference this morning. Must appreciate the fact that you're able to be part of the learning process this morning. Thank you very much. We have watched and listened carefully to the lecture, and right now maybe we still have about 10 minutes before we cross over to the next session. I would very much love to maybe in a few minutes hear from you. If there is something that has been added to you this morning through this lecture, I would be very happy to note that. I would be very happy to hear from you. So kindly unmute and speak to us if there is anything that has caught your attention this morning. But of course, as I wait for you to do that, I would also want to draw your attention to YouTube. We have this clip or this video we have watched and many more works of our Professor Joseph Ntai on YouTube. There's a lot of work on PhD workshops, navigating PhD terrain. There's a lot of work there. Also, there is a lot of work on philosophy of science and energy economics. So I want to invite you, go there, YouTube, put there, just go to your search engine and put there Professor Joseph Ntai. And the browser will give you lots of that information that you can be able to read at your own time and will be able to help you in your journey. So I want to thank you very much, and I want to, about 8 minutes or so, I would like to hear from you. What is that has triggered your mind this morning? Is there anything that you can say, okay, in this 1 hour, I will not exchange it for nothing? So the mic is with you now. So I'm scrolling through my what here, trying to see. Kindly unmute and share with us your your thoughts this morning. May not necessarily be what is coming from the clip we have watched. Could also be some ideas that you have that you think you want the rest of the students to hear. I keep telling ourselves that this 1 hour is ours for us to share and exchange. At this time, there is no expert. We are all learning. So feel free to share your ideas with us so that you never know, someone could be available to help. Okay.
Morning.
Good morning. Thank you very much. Go on, Robert.
Mine is just to appreciate you for the moderation, but also to thank Professor for putting together the pieces that we have just listened to. It really rejuvenates us and helps us to really understand the process of research, theory building, and the purposes of how to use theories to develop our concepts and putting things together. I really want to just appreciate him. And since you have given us where to find this information, I think to really do us a good justice. I continue thanking Professor for this platform. And I wish all of us to go to the next stage. I thank you very much, sir.
Thank you so much, Robert. Thank you so much for encouraging all of us. And it gives me also the strength to know that people are not actually sleeping. People are watching and following. That is very good. Thank you so much. I see on the chat here, peace. Okay. Okay. Peace. Would you want to echo on something? I'm seeing you've written some very good information here. Would you be available to re-echo on it, if it's okay with you? We can see your mic is unmute, but we can't hear the sound. I hope there's no technical problem there. Okay, we still have about 4 minutes. Would love to get one more person, and we wrap up the student session. Okay. Peace, we see your mic is on, but it appears like we can't actually hear. I hope the issue is not network or something like that. Okay, that's fine. In the remaining 3 minutes, can I hear from at least one person to wrap up this? Okay.
Mr. Lasso.
Thank you. Yes.
Since nobody is talking, allow me to say something. When we undertake this very important study, seeking for a qualification that is known as a PhD, there are a few things that we need to be mindful about. One, we actually enter a qualification or training for a qualification that will usher you into research. Actually, the entire research process starts at this level of a PhD, not really a master's, because at the master's level, you do not know what you are doing. But you start learning how to do research at the PhD level. So that means there are lots of things that you must unlearn. And then, of course, you pick new information. Two, when we embark on the research process, many of us fail to understand that there are two parts in that research. One is the theory building, right? And really, at the time when you are writing your proposal, when you are developing a proposal, you should be mindful about this element of theory building. Because when you really go into whatever you do in the background, and then you embark in the process of giving you or developing a conceptual model, conceptual or theoretical model. Because at that level, you start thinking about reality out there, right? And the various interactions of the concepts or the events that you see out there, right? And of course, what is contained in literature, right? So there is a combination of that even when you're writing your introduction. That's why I think earlier lectures, we had people like Professor Koche and others who talked to us. So when they talked to us, they told us that, you know, your background, although in some universities you don't have a structured background, but certainly you have the historical background, you have the theoretical background, you've got the conceptual background, and then you have the contextual background. All those constitute the introduction. In some universities, they do actually indicate those headings. In some universities, like ours, we don't have those subheadings. But when you are writing, some of those things really come out. Now, at that stage, at the time you got the statement of the problem, whatever you choose to write down there, up to the conceptual model, that is a theory building process. And if you have done your systematic literature review very well, right, you can actually publish a theory building paper at that stage. And of course, if you don't want to call it a theory building paper, you can call it a conceptual paper that can be published. So that is the theory building. Now, the second part is when you develop your instruments, and then you go out the field and collect data, right? And you come up where you do the analysis, come up with the results, and start interpreting results. Of course, your interpretation must relate what you have, the conjectures that you have either developed or hypotheses that you have. Whatever, if you have used propositions, you must also compare the propositions or research questions in this case. So that is the theory testing, right? So there's a lot of theory that goes into the first part, that's the theory building, that must be tested later on. But for those who want to use one theory, again, you test that one theory. For those who combine theories, again, you test because you have your conceptual and theoretical model that you test at the end of the day. So I think that's the comment I wanted to make before the main presenter comes in. Thank you, Mr. Lasso.
Thank you very much, Professor. Thank you, and thank you very much. I had a hand from Dorcas. Dorcas, may I give you 1 minute? 1 minute, we are already past our time by 2 minutes, but let me not miss that information you have for us. 1 minute, Dorcas.
Yeah, thank you, moderator. Good morning, everyone. Sorry, I came in late, but I just wanted to maybe explain something small about Peace to Shabe's comment, where she says, "Thanks, bro. I have come to know that our research is composed of 2 parts." True, professors answered that. And then she was like, some confusion. Could it be among the reasons or defense we take for critical realism? So what I wanted to say is that because we are carrying out this research, and because we actually do not know what people think about what we are studying, I think it is the reason as to why we go out to look out for that reality in terms of how do we understand it ontologically, that is the nature of reality being objective and subjective, and then also how you're going to collect that data and interpret it through the multiple views that people have given you, multiple views or opinions. And this is what some researchers call constructivism. I just wanted to say that. Thank you, moderator.
Thank you very much, Dorcas. Right now, I think I really don't want us to go beyond this, but thank you very much for your comment. Thank you for participating, and thank you for really, being there every Sunday morning and learning. It gives us energy, it gives us strength to know that you actually don't log in and go back to sleep. It's possible, then we'll be calling your name and you're nowhere to be seen. But thank you, and thank you very much. Right now, I don't want to go beyond this. I just want to call one of my seniors to take this mic away from me. Dr. Ahmad, I don't know whether you are on. Allow me to hand over this mic to you. Thank you very much.
Thank you very much, Joseph, for moderating and managing the what we call the student symposium on this platform. Thank you, Professor, also for supporting the platform from the beginning up to the end. We appreciate that commitment. Professor, we appreciate your support in a number of ways, both to the students and also to post-students level. We really learn a lot from the platform. Allow me appreciate the senior members who are here today for their contribution to research and for their commitment over time without even a single pay or a single contribution from the other side. So let me first of all recognize our senior members, Dr. Goretti-Chayune. Dr. Goretti-Chayune is very committed to the platform, even if she's not a candidate, she will try to join in. Dr. Gideon Kurunziza, who is our main presenter today, I will come back to him. Our own Professor Rola Orobia, thank you for being part of the platform, and thank you for always supporting the students community. I'm sure other professors are yet to join, but they should be joining. Professor Picho had confirmed being with us, and I know he's going to be joining soon. And also other professors and doctors, Dr. Dens, Singuzi, and many others. Allow me this morning introduce to you introduce to you our own, who is going to present, and the main presenter of the day, Dr. Gideon Nkurunziza. Dr. Gideon is the statistician. He has a statistical background, educational background, and also he has been working with Makerere University Business School for quite a while, 10 years plus, teaching statistics. He has a PhD of Makerere University, and also he is currently heading the Department of Education at Makerere University. Dr. Gideon is part of our own, and he's among the regional team of this platform. So his contribution to the platform is not only in the presentation today, but he has been making a number of contributions always to the platform by supporting a number of students. He's currently supervising a number of PhD students here in the different universities. So Dr. Gideon, we appreciate you, appreciate that commitment, and we thank you for your contribution. Those who are joining the first time, before we invite Dr. Gideon, we would like to mention that this is a platform, all students in different universities, and you realize at the moment that we are, you will note that we have universities here in Uganda, universities in Kenya, Tanzania, universities from South African region, universities from North African region, and some universities in Asia and Europe. So we appreciate all the students who are on the platform, and the students who have been contributing to this platform. We appreciate you and we thank you for your contribution. Allow me to invite Dr. Gideon Nkurunziza to take us through interpretation of correlations and regression results. And after him, then we will have a short presentation, and then later on we shall have questions from the students community regarding the same. Thank you, and back to you, Dr. Gideon. You're welcome to come and share with the audience.
Thank you, Chair. Thank you, Dr. Ahmad. And I thank our mentor and other senior mentors, our colleagues, the students, PhD students. I'm glad that today I've been given a chance to share the little that I know about this topic. Allow me to first give a preamble. Sorry. Let me first share my screen. Chair, you may confirm whether my screen is clear. The Socratic Research for Community Development.
Yes, it is clear. Just put in a presentation format.
And increase the volume a bit. He's low.
Okay, thank you very much. Let me try to be loud. Our topic is correlation and regression analysis. I know there has been serious debate on this issue. If you look at the historical perspective, a number of scholars tried to defend this kind of measure. These two measures, if you remember what happened, for those who have tried to find out what Galton did, looking at the plants, how they tend to associate with each other, where there was, it's a long story, but let me not go into that. Basically, I think I want to put emphasis on interpretation. But this debate has been going on from 1980s, and to date we are still so looking at it even today as researchers. From the social perspective, I try to relate with what exactly these scientists we are doing, these mathematicians we are doing. And I came to realize that even in our society, we use the correlation at times without knowing that we are using it. I can give an example of the field of institution of marriage. That times when you want to marry, they encourage the potential partners to visit. And at times the parents tend to look at the height of their MUCO, and they see whether the height of their son, the son of the MUCO will most likely be associated. And I think it is so serious in some cultures. I believe even when you meet somebody and you smile, another person smiles, at times you question why that association is there. So basically, I want to say that if that association is there, then you go ahead and see, maybe next time when it continues to happen, you can even tend to predict some bit of variation in your mind from the perception point of view. So ideally, this is a concept that we usually use. Even for those who are in farming, at times you apply fertilizers to see whether maybe the yields could change. And if there's a change, at times there's a conclusion you derive. So basically, I want to say that this is a topic which we usually use in research, and it is also a topic that we usually use, especially when I'm making a number of decisions between different variables. Surprisingly, when you look at correlation, from the point of research, our major emphasis is to look at association. Association between two variables specifically. And as a researcher, you need to find out what are these two variables that you tend to correlate. One, you may have a number of predictors, which we call independent variables, and a dependent variable. So if you take a bivariate kind of correlation, you correlate the one predictor with a dependent variable, another predictor with the dependent variable. Definitely see whether the relationship is there. Of course, I believe as I proceed, I will say that there are certain assumptions that you have to consider before you use these models, correlation and regression model. Why? Because this is a part of inferential statistics. There are certain inferential statistics means that you are trying to use methods and procedures where you draw conclusion on the population based on a sample statistic. Yeah, where there's some bit of generalization. So even when you have selected a sample, then you need to see whether association exists. Then when you want to look at the relationship, you want to look at the prediction. You could have established that the relationship, association exists between the two variables, but then you want to see whether the predictor variable could be able to explain the change in the dependent variable. And that is when you want to go into prediction, you want to establish relationship, then you are into regression analysis. I also know that there are a number of regression analysis you can have depending on your objective. And for the purposes of time, I may not focus at all of them, but I pay attention to the commonly used ones, like hierarchical regression, multiple regression, simple regression. Mostly, I think we rarely have studies of simple regression at PhD level. We tend to have a number of predictors, a number of independent variables to explain the criterion or the response variable. Now, surprisingly, when you are deriving a regression model, you will find that there's an assumption that you will have a constant, that if the predictors remain constant, they do not change. There's certain constant that is expected, and you also expect to have the errors, the error term. That error term is expected because as you sample, as you randomize, don't expect to find that the statistic and parameter the statistic is a numerical value that explains the characteristics of your sample, and then the parameter, which is a numerical value that explains the characteristics of population. If you look at for example, you look at the sample mean and population mean, you compare. It's very hard in most cases to find the two being equal, although it is what we aim at. It's what we aim at. So that's why the error term comes in your model. As we look at this, before you think of using these models, correlation and regression analysis, before you carry out that, think about certain assumption about your data. One, you must test certain assumptions. Of course, looking at the terms we usually use at PhD level, parametric assumptions, where you assume that there is a distribution, a well-defined distribution. And if there's a well-defined distribution, then the normality assumption must be satisfied. When we talk about normality, I think you can remember how a barrel looks like, barrel-shaped. And we expect to have a normal distribution, which we call symmetrical distribution. If you test, today I may not go into those tests, but I want to say this assumption. You must remember them, that if there is a normal distribution, then you will now think about, if you are to run a correlation, which correlation coefficient are you going to run? Is it Pearson? Is it Spearman? Is it Kendall? If you have a linear relationship, of course, all of them, whether you're using Pearson, for Pearson majorly, there must be a linear relationship. Although for Pearson, for Spearman, there's more. Of course, sometimes it's not linear, but there's that tendency of having it increasing, but not curvilinear, of course. So there's a change, but not that change, that variation, or that slope, or that change in y with respect to x, change in your dependent variable with respect to independent variable, you find that it is a bit, actually it is constant for when you have to use Pearson. But if it's not constant, please don't use that. So that assumption you have to test and see whether there is a linear relationship. Otherwise, there's sometimes non-linear relationship, that the variables, the predictor variables and the criterion variable may change, but then reaching somewhere, then you find you have a situation of curvilinear relationship, which is not linear. Definitely that becomes a limitation to apply correlation analysis in your model. The other one is homogeneous variance. You need to look at that also. When you have picked your sample, do you find that there is the equivariances in your sample and the population? In other words, to somebody who's not coming from the statistic background, do you find the sample you have, the data you have, is coming actually from the population that you really targeted? And this is where now you need to study your sample very well. There are certain characteristics that actually may cause, may make the homogeneity of variance not being satisfied. That's why, like, if you look at financial institutions, one will ask, but do they really aim at the same thing? If these are tier 1, tier 2, tier 3, so homogeneous variance, are you likely to have it? Or you're looking at university lecturers, but you find these lecturers are having different positions. So what happens? I think this is why sometimes homogeneity of variance is very, very important. I know people from economics, they use also another term, homodyscacity. I think that's the same concept. The other one that you need to pay attention to before you apply this correlation and regression, you must check whether there are no outliers. If there are outliers, what does it mean? Of course, outliers usually affect your data. Your data may fail to behave normally. And of course, there are others that you need to pay attention to. Things like you may need to look at whether maybe you don't have endogeneity bias, for example. Endogeneity bias in your data. If you have not checked for those, please don't rush. At the point of defense, they come back to you. Ideally, that's very important. So this is why I've been saying that before you run correlation analysis, and you have to make a choice between when to use Pearson correlation, when to use Spearman, and when to use Cantarus, there are certain things that you must reflect on. One, for Pearson, ideally there must be a linear relationship, as I've said. So, absence of outliers. Please, when we go through data screening and we check whether they are missing values, whether they are outliers, we are trying to predict further as we try to answer objective. If you have an object that requires you to run a correlation, you need to foresee that and see whether your correlation coefficient you are going to use is appropriate. The data you have, because if you look at measurement scale, for example, there is interval, ratio, ordinal, nominal. Nominal, especially when your data or you have a variable whose values can only be obtained by classification or categorization. Then you know that is nominal. It follows under nominal data. And at times you also find is that ordinal scale where there is some bit of ranking or some ordered relationship in your data based on the variables you have. Now, in brief, I'm trying to say that for Pearson, pay attention to measurement scale, pay attention to the relationship. When you do parametric tests, you check for those assumptions and you find there's no linear relationship, especially when you use even scatter diagram, and you don't see that linear relationship. Please, you know by the time you use Pearson is really not appropriate. And for Spearman, you need to pay attention also to parametric assumption. If parametric assumption is not really well satisfied, then you are left with another option, which is Spearman. Spearman helps you. One, it has monotonic relationship between those variables that you have considered, especially continuous and ordinal. Actually, when you have designed your questionnaire, endeavor to look at the measurement scale, please. That will guide you, especially by the time you are choosing which correlation coefficient to use. Monotonic means that at times you find that let me use the predictor to become X and the dependent variable to become Y, that as X increases, Y is likely to increase, but not proportionately. Not proportionately. So the relationship may not be constant when you look at the magnitude of that relationship, which we call in mathematics weight slope, is not constant. So unlike when you look at Pearson, that is where you have a clear distinction. However, you may have also another option of using Kentaros if you find the Pearson is not really, the parameters under which Pearson is able to be applicable is not relevant. So you have the choice between these two. I think that's basically what I can say on that. The other one that you need to look at intensively, as I'm trying to summarize it from the broader perspective, that as you think about correlation and regression analysis, there are a number of things that you must reflect on. One, right from the point of your background, your central argument, your central thesis, which gives you the purpose. Which purpose, again, guides you to know your research design, to know your theorization, testing, philosophical stance you are using. If you align all that, it will guide you to know whether in your methodology you will have to test for hypothesis. I know sometimes people, when they are working from the background, then you go to methodology, you see somebody is actually testing, he has hypothesis testing, and yet when you look at the research objectives, they do not require. Even the problem you're investigating not require. So there's need to really go into in-depth understanding of where you are coming from and where you need really, whether you need to test for correlation and regression. The issue at hand. The other one is, even when you have reviewed literature and you have used theory and you have derived your hypothesis, in your mind, are these hypotheses directional or non-directional? If they're directional and or non-directional, when you are analyzing, do you consider the two-tailed or one-tailed? When it is direction, of course, we would expect you to use one-tailed. And when it is non-directional, that could be two-tailed. But the advantage of using two-tailed, again, you will find that when you use two-tailed, it gives you the positive and negative relationship. So you find, again, the two-tailed will give you that kind of opportunity as a researcher. But when you say I'm going to use one-tailed, then you know what it means. From the statistics point of view, even when it comes to computing the critical values, you know, the approaches are different. One becomes a half of the other, looking at the alpha, which is that kind of when you are looking at confidence interval, and you consider maybe 95, So the other 5%, if it is one-tailed, then it will be a half, which becomes 2.5. But for the other one becomes. But I don't want to go in that way. My emphasis is that in your mind, as a researcher, reflect on the way you stated your hypothesis before you look at regression analysis. So that during the process of analysis, you know what should be included in your final outputs and what matters. The other one is, which we take a little bit casual in research, is the sampling methods that we use. Some sampling methods we use have got implication in on the choice of the correlation coefficient you are going to consider. Just imagine you use the non-random sample throughout at unit of analysis, unit of inquiry, and then we see you posing very well with Pearson. At times we are so suspicious that since some of those methods which are non-random have got bias, we think probably if you do not really handle your data very well, it's plausible to such a kind of issues. The other that we tend to lightly is the sample size. I know when you generalize again, I don't want to go into the T statistic and the Z statistic, but if you know that the sample size is small, at times when it is small, we rely on T statistic. But as we increase the sample size, in statistics we have the central limit theorem, that as we increase the sample size, you are likely to reach somewhere where your sample which was behaving as if it is normal again becomes normally disputed. So sometimes we question about the sample size again. Yes, you are going to run your regression, but the question is, what statistical tool are you using if your sample size is very small? And this is why somebody will tell you, I'm going to use a smart PRS. Another one is saying, I'm going to use Amos when he's trying to run structural fusion model. Yes, you are going to look at multiple regressions, but the question is, did you look at the sample size? Please, this is very, very critical. At times you see a friend using Amos and you say, I think they also use Amos, but you don't know somebody who came up with this software, there are certain assumptions that was able to consider. So if you are having a sample size below 200, why then do you go into the use of Amos? Because you know you have high measurement errors. So it is important again that you reflect on that, the sampling methods and sample size. Very, very critical as you run your correlation and regression. The other one I mentioned, I've been mentioning about this, is parametric and non-parametric assumptions. The parametric assumption, I explained them from the beginning, I think, looking at normality, homogeneity variance. I think I explained that, so you need to look at that now and you know where to go. At times I know today being correlation and regression, I wouldn't go into chi-square when to use that because sometimes when these other fail, then you have an option of going to non-parametric tests and the statistical tools that require the non-parametric data. The other one that you may pay attention, I mentioned about measurement scale, but in addition, we need to pay attention to measurement units. When you're interpreting your regression, and also correlation results, pay attention to the measurement units. If your independent variable is measured maybe in meters, and your criterion variable, which is the dependent variable, is measured in kg, kilogram. Now, when you are looking at the magnitude in terms of the variation, where the predictors are trying to cause a change in the other dependent variable, how are you interpreting the results? This is why sometimes you may be forced to transform the data. Now, for those who come from mathematics, statistics, and economics, I think for them this is not an issue, but majority of us who come from other kind of discipline, at times we don't pay attention to these issues, and these questions keep coming even towards the end as one is concluding the journey of a PhD. So if you say I transform, there are a number of reasons why I transform. Maybe you want to remove those elasticities in terms of measurements. I think that is very important to reflect on. So today, this is the concern mainly that as you look at interpretation of correlation and regression, these are some of the also the other aspects we may need to pay attention. What is the meaning of R? When you are looking at, for example, a simple regression, and when you're looking at multiple regression, do they mean the same thing? What about the R squared? What do they mean? What about adjusted R squared? What about the R squared change? And what about F statistic and the T statistic? The beta values, those which are standardized and not standardized, and then of course when you use hierarchical regression and multiple regression. Mainly this is where I was able to focus based on the topic that I was given. The other one was part of preamble. And I would like to, I have a set of data set. Maybe I run this and we see how we can make a meaning of the results that we generate together in this session. Chair, I don't know, I'm not reading through the chat, but I'm seeing there are 9 comments. Before I go to the process of analyzing data interpretation, Chair, you can guide if there are some comments that require attention before I proceed. I think that could be fine.
Dr. Gideon, not yet at the moment. I think the comment we have that is to you is that they like the presentation so far, and they would like it to be given to them at the end. So I think we can go ahead and do the analysis and then interpret the results.
Okay, thank you very much. Let me try to So I have the data here. I think let me try to share. This data is in Excel. As I look at this data, please try to reflect on your model. In this, I seem to have I have the dependent variable, which is shipping price. And this shipping price, in my theorization, I'm looking at the mass, delivery time, distance covered to be the key predictors. Perhaps to explain the shipping price. And I believe also you have also the conceptual models, or you have mathematical models. I know the conceptual model can again be translated into mathematical model. So if you reflect on what you have, you can now be able to pick the dependent variable and the predictor variables. And so these are some of the observations that I have for each of the predictors, as well as the criterion or the response variable, or the dependent variable, which is the shipping price in million. Now this work is in Excel, and I'll be able to export it in spaces. I know I think the choice of what to use again depends on the reasons you have. So you can use Stata, you can use Amos, you can use spaces with clear justifiable reasons. And whichever you use, you'll still come up with your regression model and your correlation model. Now, if you maybe I don't know whether I can do something. Chair, I don't know. I wanted to use webcam, but I think it is refusing. I think let me leave that. I wanted to use webcam, but I think I did not test it. Sorry, I think webcam is refusing. I have not tested it before. Let me just explain, and we look at it directly. Now, what I need to do is now to export this data from Excel to spaces. I know most of us these days, because of even the technological advancement, you can gather your data using computerized tools. Either you are using Kobo Toolbox or using Google Form, and then you can export your data from Excel to spaces. Now what happens that I can open my spaces file. If I open spaces file, statistical package for social scientists is a statistical computer package we can use to analyze our data. The advantage with it is user friendly. If you're not used to those commands and you're not used to R, there's R programming, or you are not used to Starter, I think still you can use spaces. It can generate for you the results. So if you open the spaces and then you export, let me open it, then I export this data. I know it takes time because it is a bit heavy. It is still opening, but it will come. Chair, is my screen being seen as it is opening?
SPSS is still opening. Hopefully it's opening soon, but SPSS is opening.
Okay, thank you. So I'm assuming this data, although it is now in my PC, it is already open. But if you are now opening it for the first time, you can go to Open. You go to File. After going to File, you choose Open. Then you go to Data. Data. The cache is still inactive. I think it is still on my side. It's still opening. When the cache is ready, you can go to Data. After going to Data, you reopen the data. But of course, because your data is saved in Excel, what you do, you reselect Excel. I hope it is now ready.
Dr. Gideon, we can't now see your screen.
It has stopped. Has it come now?
It is loading, but we haven't seen it.
Okay, thank you. Now, of course, what happens that I hope you are seeing it.
You can first open your what on your screen, the file, and then later on share. But if it is not on desktop, it will be very hard for us to see.
Thank you, Prof. I was going through the method of how to arrive there. So it is on desktop, and we can choose desktop. However, because it is in Excel, then we can now select Excel, and you shall see it. It is this one here, Socratic Research for Community Development. That's the data now, which
We are not seeing anything.
Hey, sorry.
Doctor, we are not seeing anything this side.
Hey,
We're only seeing your folder for documents, videos. Okay, something has come.
Up to now, it has not come. Okay.
We have seen something now. Distance covered.
Okay, thank you very much. I think that is the document I've been opening. And so we are going to run the correlation and the regression. We start with the correlation. Now, depending on why you are running correlation, we said correlation, you want to check whether there is association between the two variables. Two variables, the dependent and independent variable. Now, in my data, I have three predictors: x1, x2, x3. X1 representing distance covered, x2 delivery time, and x3 the mass in kilograms. And then the predictor variable is y. Now, you need again to check why are you running this analysis. At times you find that when you have your objective, perhaps they could be answered by regression model. But then you may need maybe to check whether there are issues of mitochondriality. You want to see whether the correlation is high. If it is high, close to from 0.7, 0.8, 0.9, at times you should get worried. What is the problem? What is the problem? Is it okay? And then in your mind, you should also be aware that when you do a regression and you look at the total contribution that is explained by the predictor variables on your dependent variable, and you find it is close again to 1. 1 in terms of percentage, that's 100. You have 90% being explained by your predictor variables. I know most people celebrate, but I think instead of celebrating, you should be worried. Because if you picked these predictors from the scholarly work, in the context of your study, do you think these are the only predictor variables that explain your dependent variable? I think these are a few things you must have in mind as you do the analysis. So we can now go through the correlation. Depending on, again, the other factors that guide you which correlation are you going to run. So you can go to analysis, then you go to correlation. We want bivariate because our interest is to look at the relationship, the association between the two variables. Now, this is where you find now you have to make a decision. If from your theory testing, you wanted, first of all, you had the non-directional hypothesis. If the non-directional hypothesis, then you have to select the two-tailed. Non-directional hypothesis is where you say that, I can give an example. You say X is associated or is related with Y. You don't want to commit yourself. Why? Because when you reviewed literature, you got some kind of inconclusive debates, and therefore from what you have derived, depending on which approach you have used, whether you're using progressive, sensitized coherence, or the non-coherence, and you have reached a certain level where you are deriving your hypothesis in your literature. Now, you left that hypothesis taking two positions. And so you have not really decided to say it is taking a positive direction with the X and Y, or with the predictor and the dependent variable. That's when you go to tail. But when you know, you are very sure that it takes one kind of direction, one side. X is positively associated, X is negatively associated, then you know where to select. The other one is that, again, looking at the other assumptions that certify the use of Pearson, that's when you select Pearson. If you also realize that those assumptions do not work for Pearson, then you can select Spearman or Kendaros, having seen when do we use these ones. Now, my interest now is to look at the correlation of these variables now. So I can select all of them. And if the data satisfies the requirements for Pearson, then I can use Pearson. I select Pearson. And if I wanted to look at the means and standard deviation, in addition to correlation coefficient, then I can also select that. Now, you need to select flag as significant correlations. So that by flagging this, now the software will now determine if the association is significant. It will determine whether it is significant at 95 level of confidence, at 99 level of confidence, at, of course, depending on level of precision, it will show you definitely. So if you click OK, then the results will come, the outputs, which I believe you can't see now. Let me try to again share them. Do you see the outputs, Chair?
We are seeing them.
Okay, thank you.
Yeah,
so when I use this correlation coefficient, basically relying on Pearson, this is what I see. You find that this one, you take a matrix, for example. If I look at delivery time, okay, the first time is the first one, distance covered with a predictor with the shipping price. You can see that a Pearson is 0.126, and this 0.126 is not significant. Is not significant. Now, for delivery time with the shipping price, it is significant with 0.837. Now, of course, if this was primary data, secondary data, I know people from economics usually celebrate because looking at the variables you are looking at the measurement scale, if it's a ratio, at times you are not worried about those most likely issues. But in primary data, you get 0.837. At times, you don't celebrate. The correlation is significant, but you can see it is high. You need to now think about multicollinearity test and see whether perhaps those issues are not coming in. which could explain why this value is high. The other one is the mass. The mass with the shipping is also positive 0.281. Now, what does it mean? What does it mean when you are trying to explain? It means that a positive change in delivery time.
I don't know whether the problem is on my side.
Yes, please. Hello.
Professor Rola, Professor Picho, are you hearing the?
Yes, we are hearing him, and also we are seeing the output.
Thank you.
The problem could be on your side.
Thank you. I'm also hearing you, all of you, I think.
Okay.
I think my side is fine. I'm saying if you look at this correlation coefficient of 0.837, since you know correlation brings association, and association, at the level of association, you're not sure whether you can, association does not really imply causation. Now, I think this is also why I need to emphasize that earlier we said you must be aware about your research design that you use to gather this data. If you used cross-section research design, that means you gather data at a point in time. And therefore, you are at association, you're not in causation. But if you did an experiment, then you can now interpret your correlation in terms of causation, because there are certain factors you controlled for. And if you did a longitudinal kind of study, and you had the data which has been observed over time, either you are basically using panel data, you are using time series data, but again, which has not been based on cross-sectional kind of research design, there you can go into causation because something has been observed over time. Experimental research design, longitudinal studies, then you are more into causations, but cross-sectional, you are in association. Therefore, the way you interpret your correlation coefficient will again be well aligned from where you're coming from with your research design. So this means if this was an experimental research design that helped me to gather this data, that aided me, that means I can interpret this in terms of causation. It is probable that this delivery time has really caused this kind of change. In other words, it's not associated. It's related now. I can now even use a relationship now at this level, if it is experimental research design. But for cross-section research design, we can say delivery time, a change in delivery time is associated with a positive change in the shipping price. And this is explained by correlation coefficient of 0.837. The mass, again, a positive change in mass is also associated with a positive change in shipping price, as explained by correlation coefficient of 0.281. So most of our studies that are cross-sectional research design based, we remain in association as we talk. In other words, the language you are using, the tone you are using should show that you do not reach at the point of looking at causation. So basically, I think I have looked at the predictor with the with the dependent variable, but it depends on how you have stated your objective. If your interest was to look at distance covered with delivery time, you would look at the correction coefficient of 0.168, and it is not significant. Not significant doesn't mean that the association is not there. It is there. But this association, again, depends on the sample size. Ladies and gentlemen, as we talk about the significance level, that significance level depends, again, on the sample size that you have. You can see here I'm considering 50 observations. 50 observation. Perhaps when you change this observation, these results may change. So the association is there, but not really very significant in the context of this study. So that is what I can add. The other one now, if you wanted also to do, you wanted to run again the correlation using Spearman. You can follow the same procedure. Correlation of looking at Kentalos, you can use again the same procedure. So let's now look at the prediction. We have seen that association exists. Can we go ahead and see whether these predictors explain the dependent variable? In other words, whether distance covered, delivery time, mass, whether they all predict the shipping price, whether maybe one is not so important, another one is very important. And this helps even when you are coming up with possible recommendations. Which one is the key? Where do you put much emphasis as you are trying to make a conclusion? So the regression is very, very important. It will tell you which one is very important in explaining, or is significant in explaining the shipping price. And that is when we do a regression. Now, again, the choice is between, I think the choice will depend on how you stated again your objective. If you wanted to look at the contribution of each of these predictors, then it means that you can now enter each variable, each predictor variable at time, and you look at the contribution of each, and that requires you to look at hierarchical regression. Now, if the shipping price again would have some bit of binary outcome, I know for those who come from pure statistics, talk about survival analysis. Yeah, when you're looking at treatment and somebody is to survive and others to die, then you know there are basically two outcomes. Again, they also dichotomous kind of studies, especially where you have the binary outcome. There are two possible outcomes measuring shipping. Then you talk about logistic regression. You can use logistic regression model again as you are running the regression. Then, if you want to know you want to combine all these predictors and you want to see the contribution of all of them without basically focusing on the contribution of each, then you can use multiple regression. I know there are other correlation models you can derive, but basically for today, let me focus on majorly the multiple and hierarchical regression. Then maybe later, if chance comes again, we can look at others. We can now run the regression. And I want to start with the multiple regression. Multiple regression, meaning that I'm going to consider all variables at the same time. being in the model. And my interest is to look at linear, because you remember even some of the assumptions we considered there linear relationship exist. So if linear relationship exists, you carried out those assumptions, then you must use linear regression model. Our dependent variable is shipping price, and the predictor variables are these. Now, in this model, we don't have control variables, but sometimes, depending on how you have conceptualized, you may find that in our conceptual, as you conceptualize, you found that literature again tells you that some of either individual characteristics or organizational characteristics are very important. So you may also want to introduce them, and you see whether their views perhaps can also help you to inform your study, or whether you can dismiss them basically based on the data that you have. So in this case, since I'm looking at multiple regression, I can bring in confidence interval. If I want, by the confidence interval can tell me or can tell you whether your beta values or your predictor variables are important or not important, by looking at whether zero lies between those confidence limits, upper and lower. If there's a zero, what does it mean? If there's no zero, what does it mean? All that also can help you. Since I'm looking at multiple regression, R-square change doesn't matter here so much. Coordinated diagnostic is important if I want to look at the relationship between these variables, and again I want to see whether there could be some of the multi-coordinate issues, maybe hidden. There could be hidden kind of points that are explained by certain variables, which were not very important initially in my conceptualization, but can be there again for me to deep further and know how to deal with them. Davidson-Watson, this one is good when you're looking at the longitudinal studies, and you can see this one, if it is cross-sectional, it doesn't make much sense. So basically, that's what we have here that is very important. So we can click OK and we see what happens. Let me again share what I've found. I hope, Chair, you are seeing the output now. May I confirm?
Yes, we can see it. Yes, we can see it.
Okay, thank you very much. Now, I have rushed very fast. I've rushed very fast to bring all the predictors. Now, if I rush very fast to bring all the predictors, this R is for multiple regression. What is the message about this R for multiple regression? If it was a simple regression means you just consider one independent variable and one dependent variable, and you regress them. When you regress them, the correlation coefficient for x and y in that case will be equal to this R. It will be equal to R. They will be equal. But now for here, for this case, since I introduced all the predictors, what does this big R mean? It means that the observed values values, when you correct observed, it means that this R is the correlation of the observed values of x1, I mean, no, not x1, of y, and the predicted values of y, which y is the shipping price. How do you get the predicted value? It means you must have derived the model. When you derive the model, you keep on substituting the observed values of y in the model. And then, I mean, of these values of x, you keep on fitting the model using these values, and then you'll be able to get the computed values now. These computed values are the ones that you correlate with the observed values now. What you observed at first, and then when you substituted the values, you got the predicted values, and then when you correct them, what you get is this capital R. Now, the R square is the square of this R. Now, the correlation between the observed value and predicted value of the dependent variable. Now, when you square this capital R, you get R squared, which is we call it coefficient of termination. We call it coefficient of termination, which shows, what does it show? It shows the contribution of these other variables on the shipping price. That 74.1% which is a variation in the shipping price, is explained by the change in these other ones, by the delivery time, distance, and the mass. Now, we also have adjusted R. Now, what you need to watch is that when you continue introducing the predictor variables, assuming you add other predictor variables in the model, you increase the predictor variables from 3 to 4, 5, 6, and you keep watching what happens. The R square will keep on increasing, but the adjusted R square will increase only when those predictors that you add are significant, meaning that this adjusted R square is more robust in this case, because when you consider this, we are just looking at the contribution of the predictor variables that were significant in the model. R square brings everything, whether the predictor is significant or not. It tells you the contribution, even the one which was not very important. But adjusted R tells you the contribution in the model, and it also tells you that this is a contribution of those variables, predictors, that are very key in explaining your dependent variable. And the other one, which is very important again, is this F statistic. I had thought I'd demonstrate using webcam, but I think that can't work. F statistic will show you that if you are going to use your model for prediction now, you are using it for prediction, then is it good enough? We usually use the terms goodness of fit. Is the model good enough for prediction? By the way, why do we call it a model? We call it a model because we have derived an equation. We have derived an equation by bringing the beta values, which I'm going to explain later, to make a forecast. But then the data is not from the whole population, it's from the sample. a model is something that becomes reality. We have different models. So these are mathematical models. If you form a mathematical model, it's something that, again, you can use it for even when you're looking at the bigger population. So therefore, before you use it, use the model for prediction for the whole population. The question is it good enough? And that it is good enough when the seed level, this value is less than either 5% if you are considering an 95 level of confidence, or it is at 1%, which is the same as 0.01 if this value is than 0.01, then you can now consider this to be statistically significant, meaning that the model is good enough for prediction. Which model are we talking about? The model we are talking about is that model that you can now derive. You can even have y is equal to x1 b1 plus x2 b2. Where is b1 now? It depends on how you are going to name them. That distance covered, your beta now here is negative 0.230. Delivery time 0.806, and mass is 0.658. So this is unstandardized. Now, the fact that these are in different units, if you are interpreting, you interpret in relation to the units you are using. Otherwise, if you don't do that, then you go to standardized, which standardized again brings in the standard deviations now. And I think when you go in standard deviation, I think you are going to a little bit the area of the central limit theorem again, because how far is the x values deviating from these other values. I think basically for me, if you are not so good in statistics, you just explain these, but as you explain them in terms of the units that you have. For example, if you look at the distance covered, the beta value is negative 0.30. What does it mean? It means that a unit change in the distance covered, in other words, the unit change in distance covered, of course, makes a change in shipping price by 0.23, and in other words, as this one increases, this one reduces by 0.23. Now, if you want to do it very well, you can actually form an equation, and if you remember the derivatives, you just differentiate. But differentiating, you're looking at change in the dependent variable due to change in the distance covered. In other words, if this changes by certain units in a kilogram, what happens, the change in the shipping price in millions of dollars. That's how you interpret it. And then this other one is the same. The change, unit change in time, in hours, of course, explains 0.806 change in the shipping price in $1 million. Now, the challenge comes that if you are a researcher and you want to really look at the magnitude, looking at the relative magnitude for all of them, at times you may not really generalize very well because the units are different. Now, this is where at times you are forced to transform your data so that you are able to standardize everything in the same units. I think that is what it means. Now, to know whether these values are significant, you can again look at significant levels. And then when you look at significant levels, you look at whether these sig levels are less than 1% or 5%. Now, in this study, you can see in terms of at 95 level confidence, we are taking delivery time and mass to be the predictors, the key predictors of the shipping price in $1 million. Now, you can see even when it comes to 95 confidence interval, the lower boundary and upper boundary, where you find that the zero lies in between. Again, if zero lies in between, like here, this negative 0.940 and this one positive 0.480, meaning that there's zero in between. If zero lies in between, then you know that value of beta will not be significant. But when you see these other ones, there's no zero in between, no 0.656, 0.956, 0.165, then 0.1151. There you see that there's no zero in between. And that means it is fine. You can also look at t values. The t values also behave. Now, t values, when you're using them, please be very careful, because at times the t, if the sample is very small, again, you can't expect the z-score, the z-statistic to be very, very relevant. At times, you rely on t-statistic because your sample is very small. And so at times, it tends to be somehow to behave normally. But as you keep on increasing the sample, it again comes to the level of the z-statistic, and then you have a normal distribution. And in statistics, the debate has been to 30. That if the sample size is around 30, somehow you survive. But we are lucky that the new softwares that are coming in, like Smart PLS, takes care of the small samples as low as even 12 observations. However, of course, I'm also aware that we must be conscious whenever we are choosing the statistical package to use. So basically, these are the few observations we can rely on. Other than that, then allow me also run a hierarchical regression. This was multiple regression. So, Chair, I hope now it's fine. Let's look at also the hierarchical regression. Hierarchical regression, from the word hierarchy, it means that you are entering the variables at different levels. That you need to know which variable do you enter first. If you have you decide to enter distance covered in the model, that will be model 1. In a model 1, you have introduced this variable. Now, when introduced when introduced the predictor variable in the model, there are things you have to check. Is this variable, did it predict? That's 1. 2, how much did it contribute? Yeah, I think that's what you need to look at. So we can now look at analyze, and then we go to regression, linear. Now I can reset now. When I reset, then I'll be able to start afresh. The predictive variables, there are 3. The dependent variable is 1, which is being priced in $1 million. Now, in the first model, I can decide to enter the distance covered. Now, I need to look at R square change. It's very important. even collinearity diagnostic format quantity, I can also put there and I see how it behaves. Now, in this case, I now enter it there. Then I introduce another predictor variable in the model, which is delivery time. That is the second model now. The third model, I introduce the mass in kilogram. And then from there, I can click OK, and I see what happens. So this is what happens now. We can see the model summary. The model summary brings you can see on the model, we have the first model, the second model, the third model. It gives you R, it gives R squared, it gives adjusted R squared. Now, the emphasis here when you use the hierarchical regression is what matters. Why did you use hierarchical regression? Your emphasis was to look at the contribution of each of the predictors, meaning that where you need to pay attention is in R square change. R square change. The R square change, for example, in the first model, where we introduce distance covered, we can see the R square change is 0.016. And that means when you express this value in percentage, you will have 1.6%. So you see that distance covered contributes 1.6% variation in the shipping price in million. Now, the other one you see is in the model 2, when we introduced the delivery time, which is our x2. Now you can see the R square change is 0.685, and that means the contribution is 68.5% change in the shipping price, as explained by the information relating to the delivery time. So delivery time is key. Now the other one is again to look at the model 3. The R square change is 0.041, so the contribution here is 4.1% change in the shipping price, as explained by the change in, or as explained by this information which we had on the mass in kilogram. Now, then you can pay attention to the sig F change. That when introduced the model, like for example in the first model, if you look at the significance of F change, you can see this one is above 1%, is above 5%, meaning that it's not significant. But you see, when introduced the other model, in this model, the delivery time, you can see it became significant, meaning it is very important. Then this other one again, it also showed that it's very important. As look at this last column, the last column, where we have the significance of F change. That yes, when introduced it, how did the model look like? Did it improve? Did it behave well? Yes, it did at 95 level confidence, taking the precision of 5% as acceptable error. So I think that is fine here. The other one that is also key is when we go to this other one of coefficients again. when you go to coefficients again, you have to look at in mode 1, why did you introduce? What happened to the beta value? Did it change? Was it okay? In mode 1, you can see the beta value. Was it okay? I think when I look at it, there's no star. There's no star. And even if there's no star, where the star coming from? Look at the sig level. The sig level, you can see, or the t value, you can see this is less than 1, the t value, but this sig level, again, 0.384 is greater than 5% and also greater than 1%. Even if I'm taking at 99 level of confidence, or I'm taking at, I'm considering this to be significant at 95, even other could go to 90. I think you can see that still you are not safe here. Now in model 2, you can see when it comes to delivery time, the beta is 0.821, but when it comes to sig level, it is 0.000. This value is less than 1%, is also less than 5%, meaning that's significant. So you can see that again, when introduced this in the second model, the delivery time is important. It explains actually a change in the shipping price. Now the other one is in model 3, we see in the mass 0.658. 0.658 is a beta, which is a variance in the shipping price that is explained by a unit change in mass, and it is also significant at 5% level, which is at 95 level of confidence. So you see that that's very important. The same thing you can see 95 confidence interval levels, looking at lower boundary and upper boundary, you can see again where the sig level 0 does not lie in between. So still you find that there is that kind of confirmation to see whether these values you are picking or the predictors you are picking to be very important. If you want to provide evidence-based policies, these can support your argument. The other one that I did not pay attention to here is the tolerance. Remember, the tolerance is the reciprocal of variance inflation factor. Now, the debate is there. This VIF helps you to check for mitochondrial issues. Now, the moment you find the values are above 3, sometime back we are debating about 10. This time the debate is looking at 3. If VIF is 3, then you should be worried about, you should be able to check whether you have issues of mitochondriality. So basically, I think this is important. How to compute for T statistic, these ones we have not gone into that for the purposes of the guidance I was given, interpretation, not to derive. I hope so. So basically, Chair, allow me to stop here for today, I think.
Okay,
I thank
you very much.
Listening to me. I hope the communication has been effective. Thank you very much. Chair, hand over.
Thank you very much, Dr. Gideon, for that elaborate discussion on the interpretation of correlations and regression results. Allow me at this moment to appreciate also the senior colleagues who are with us today, especially those that came in late. Professor Picho, Epifani, thank you for joining and thank you for being us from the beginning. Professor Rola Orobia, thank you for your usual commitment. Dr. Bashir, Dr. Ibrahim Musenze, thank you very much for the support and being available. It's now time for us to ask Dr. Gideon a few questions. If you have any other burning questions from on the same area, please put it forward. We have a number of professors and doctors online who can give support in answering these questions. Thank you, and allow me now go into the Q&A. Teresa is thanking Charles Kalinzi. Kalinzi is saying, is it advisable to first convert and save the file into CSV file before importing it, or it's better to use Excel? Okay. Allow me, as the questions come in, to request the senior colleagues, those who have something to add to Amin, and then we can also go into the Q&A. Let me invite first Professor Antai to give his contribution towards interpretation. Maybe in his contribution, some question may be answered, and then I'll give a chance to Dorcas and Teresa. Thank you. Professor, you're welcome.
Thank you very much, Chair. I hope you are hearing me that side.
Yes, you are clear.
Yes. Chair, I want to thank Gideon for the job well done. Let me add a few things to what he has said. I hope, is it okay, Dr. Walugeme, if I use about 5 to 7 minutes?
It is very okay, Professor. We are still within time.
Okay. I will focus on interpretation, not really the technical bit. I'll restrict my submission to correlations. I will not go to regressions. When we are interpreting correlations, the number of things that we need to be mindful about, a few things that we need to be careful about. Number one is that the correlation coefficient, whether you are calling it Pearson, whatever it is, provides an indication of the linear relationships between variables. And when we talk about linear, we are talking about straight line. Now, of course, in situations where two variables are related in non-linear fashion, right? Like where you have curvilinear relationship, Pearson correlation will seriously underestimate the strength of the relationship. And that's why we are advised always to check the scatter plot, particularly if the values obtained are low. So that is one aspect that we need to think about. Two is the issue of outliers. We need to be mindful of this element of outliers, because outliers can have a dramatic effect on the correlation coefficient, particularly in small samples. And when we talk about outliers, these are values that are substantially lower or higher than the other values in the data set. So it's always important for us to check the outliers, because these will certainly affect the correlation. The third aspect that we need to be mindful about is that you should always be careful interpreting correlation coefficients when they come from only a small subsection of the possible range of scores. For example, if you are studying university students and you pick a small set or small sample, right, from a subsection of the possible range, you will have a problem in this case. The fourth element, I don't know whether it is still third or fourth, but it's the issue of causality. And I know that, and I've seen many students moving into that direction when they see a significant positive or negative association. They rush and infer some kind of causality. So correlation provides an indication that there is a relationship between two variables. It does not indicate that one variable causes the other. And we need to be mindful about that before we rush and start attaching percentages. The other point is that when you get a correlation coefficient that is significant, we should never get too excited. Don't get too excited, because with the large samples, even a quite small correlation coefficients of, let's say, R is equal to 0.2 can reach statistical significance. And of course, although statistically significant, the practical significance of that correlation of 0.2 is very limited. So if you're using very huge samples and you get these small values and they are statistically significant, you need to be very careful. Don't rush and get overexcited. Now, of course, the other aspect relates to what Gideon has been talking about, the assumptions. Before you rush to use one particular correlation coefficient, you need to be mindful of the fact that the level of measurement matters in this case. And when I talk about measurement, I talk about nominal, ordinal, ratio, and interval. And sometimes we overlook these things and we rush and start entering variables where you have the dependence and whatever it is, and you compute your correlations. Even for regressions, by the way, it's the same thing. So we need to be very, very careful. For example, and here I'm emphasizing because Gideon did say this, Pearson correlation is designed for interval level variables. So if you have continuous variables, then use Pearson correlation, right? And I know that can also be used if you have one continuous variable and one dichotomous variable. It is also possible, right? For example, if you have scores, and that's the continuous variable, right, against things like sex, male, female, right, you can actually run a Pearson correlation. So you need to be mindful about that. And even if you decide to mix them up, at least you should know what correlation you should have for the type of data that you have so that you can defend your decision to mix them up. Otherwise, don't display at least a level of ignorance that you don't know why you have Pearson and why you have Spearman. So having said something about Pearson, let me now talk about Spearman. Now, Spearman raw is designed for use with the ordinal level. Ordinal level. So if you have ordinal data, then you can actually use Spearman raw, or sometimes ranked data. And of course, this is particularly useful when your data does not meet the criteria for Pearson correlation. So if you discover that Pearson correlation cannot work for you, then you use Spearman's correlation, right? But I've told you the circumstances under which you use Spearman correlation. Now, let me also turn, because when you go to the software that Gideon has been talking about, has been using, especially SPSS, and you go to the correlation section, there is a third correlation, right, that is mentioned there. That is Kendall's tau B, right? Kendall's tau B is used for ranked data, right? If you have data that is ranked, then use Kendall's tau B. Actually, it's the best, right? Because where you have ties, Kendall's tau B solves that problem of ties. Spearman may not be able, although you can also use it for ranked data, it may not be able to solve that problem. It is only Kendall's tau B that will help you deal with the that problem of ties, right? So that is something that I wanted to add. Now, there's a third element that Gideon did not talk about, right? That I will show you briefly. But before I show you this, I want to tell you that we also have partial correlations, right? Partial correlations. And the partial correlation is similar to Pearson product moment correlation, except that it allows you to control for an additional variable. So I know the types of correlations you're running most of the time are what we call zero order correlation, or what we call bivariate correlation. And we usually stop at that level, forgetting that we also have other statistical estimations that we can run. And that's where you have partial correlation, right? So partial correlation is usually used, right, in situations where you feel that the relationship between these two variables could be influenced by another variable, right? If you take an example of what Gideon used, marriage, for example, right? X wants to marry Y, right? You may think that what will affect that kind of relationship is the way these two people interact, X and Y, right? But that may not be correct. The parents may also come in. They can actually determine the strength of that relationship. Yeah, and in many cases, they might actually say, you cannot get married, right? Unless you decide to rebel and go ahead and make a decision. But they have told you that they don't want that kind of thing to go ahead. So in such a situation, you've got another variable coming in. So those variables can be many. That's why you can have a one-order correlation, right? A two-order correlation, that is beyond now the zero-order correlation that we know. Zero order, right? Zero-order correlation is a bivariate correlation between two. You don't have another variable coming in. But you can have a one-order correlation, a two-order correlation, three-order correlation, four-order correlation, up to the nth term. Right, the decision is actually yours to include as many as you can. So, partial correlation, as I've already told you, allows you to bring in another variable that you suspect might be influencing your two variables of interest, right? And of course, when you do this, you statistically remove the influence of this confounding variable, right? And when you remove the effect of this, or the influence of this confounding variable, you can get a clearer and more accurate indication of the relationship between your variables. So let me just show you briefly. You will excuse me, but allow me to share a bit. I hope you'll be able to see this just in a second. And I will end there. I will not really spend too much time talking about this thing. So let's just imagine that that is the SPSS data file that you have, right? And therefore, you go to analyze because you are interested in a correlation, right? So the bivariate is what you see there. So you can have any two variables here, and then you can talk about these two, the way they are related. And of course, depending on the level, right, of measurement, you can use either Pearson, as I've already said, you can see that here. You can use Kendall's tau B, and you can use Spearman, and I've already explained these ones. So don't simply bring the things here and you click anything, because whatever you click, you'll get results anyway. Right, again, there is a two-tailed down here and one-tailed, right? The two-tailed and one-tailed will depend on the way you stated your hypothesis, right? If they are directional hypothesis or non-directional hypothesis, right? Again, as you can see here, you've got bootstrapping. There are options here. You can get your means if you want, all these kinds of things, right? I'll not go into that, but bootstrapping, you can also bootstrap, right? Perform. So in this case, I'll not perform that, but I think we should have another session to talk about some of these things, like bootstrapping. Why should you bootstrap, right? Again, it is it really depends on the statistical theory, right? But most of the things that we do, we don't bootstrap. And yet bootstrapping is really very, very good. But let me leave that direction. So you bivariate, that's what you do, and you get your figures there, right? And you can always, I'm sure the output will be coming in soon, right? Now when, oh, sorry, I may have to again and share the other one for me to show you the outputs, and that's how this thing works. So let me unshare and then show you the other one, the output, right? So just to show you, that is what you get, that's the output. Right, now if I go back, right, sorry, where is my data? Yes, my data is there. We go to, again, analyze, right? Oh, sorry, I have not shared. Oh, share screen. There we are, right? Our data set. Are you seeing anything there?
Not yet.
You know, this thing can misbehave, right? Okay, let me see. Let me just go back here on the data set. Yes, we do this, share screen. Let me do this, share screen. I'm sure now you are following that. Right.
We're seeing the output.
We're seeing the output. Okay, I've now removed it. Just a second. I think my computer is misbehaving here. I don't know what has happened. I just wanted to show you the bivariate. I think something has gone wrong here. But okay, data, I'm getting there. Yes. Let me close this. No. Yes. I think now I can share this one here. A second. Oh yes. Are we now there? We now go to the to analyze, right? You go to correlation, and then you go to partial, right? Again, you can choose any two variables here, right? You enter these two variables, right? But you control for this effect of the third variable. So when you control, you get results. Now you compare these results with the earlier result, right? Now you see, I think in the earlier one where we had the bivariate correlation, R was, oh, you're not seeing.
You need
Again,
to share
let me, no, you are not seeing the results.
Yeah, you need to share the results.
Then I have to unshare again. Just a moment, then you share the results in this case here. Right. So you share the results. Now, when you run, you see here we've got control variables, right? And you've got the two variables there, right? So you see that in the earlier one, we had an R of 0.64, right? And this one here now we've got a figure of 0.54, but they are both significant, right? Of course, our sample size, our N is still 166. If you clean your data, your N will be consistent. You have a consistent N throughout. So how do you then interpret, right, the partial correlation results, right? Now, remember what I told you, what it does. Partial correlation allows you to explore the relationship between two variables while statistically controlling, right, for the influence of another variable that you think might be contaminating or influencing the relationship. So in other words, you try to get rid of, right, that effect, that contamination of the third relationship. So in our case here, since we've been dealing with the generational work values, I think that's what you saw in the leisure rewards, right? So you use partial correlation to examine that relationship while controlling for personal interest, for example. Now, when we conducted the earlier, the bidivided correlation, we discovered that there was a strong positive relationship or correlation between the two. R was 0.62, right? So now when we introduce this one here, we also discover that the relationship is significant. So in this case, we say that there's a strong positive partial correlation between generational work values and racial rewards, controlling for personal interests, right? So the implication here is that with high levels of generation work values being associated with the higher levels of racial rewards, then your S here, which is personal interest, really has no significant effect on that relationship. So that is what we do. And Ahmad, that's what I wanted to add to what Gideon has just presented. Over to you.
Thank you very much, Professor, for that add and for your contribution in enabling us understanding more on issues related to correlations. Right. Professor has some contribution in the chat, and Professor, can I request Professor to also unmute and say something so that he can really sound out her contribution? Professor Rolla.
Gideon. First of all, I would like to thank Professor Ntai for his submission and clarification of a few things here and there, and Dr. Nkurunziza for the wonderful presentation. I was just adding my voice and saying that when you run a correlation, yes, sometimes what comes out as significant relationship or association eventually in the regression turns out to be insignificant. That is also something to note. And then many times when students are presenting their results, we see very high correlations. So I was just emphasizing that when you get those, pay attention to the values in your correlation table. Pay attention. Sometimes those high correlations can be very misleading You may settle that, yes, there's a very strong association between your variables, but when actually there's some noise in the data, sometimes the data could be dirty. And there is, we have experience with students after capturing data into SPSS, straight away they run into the analysis. They do the descriptives for the sample characteristics, then immediately they go into computation of the variables. After computation of the variables, they run the correlation and regression without first having to clean the data. Data cleaning takes time. It takes time, and sometimes you have to go back and forth, back and forth, back and forth. So the high correlation may be attributed to existence of missing values and outliers. Sometimes if at all we do the MVAs and checking for the outliers, sometimes we just rush. But if you go through the process patiently, that is the most delicate part and annoying part as well. But if you go through the steps patiently, you are able to rely and trust the results that come out. So the take home here is, when you get high correlation, do not get very excited. First go back, first ask yourself, did you run a missing value analysis? Did you check for outliers? If you did that, you may probably have to go back again, this time very slowly, and establish. You'll see there'll be a change. Yeah, that's from me, moderator, and back to you.
Thank you very much, Professor. We have a few other questions, but we are running out of time, unfortunately. Allow me request Dorcas. Her hand has been up since. After Dorcas, Sylvia, and then thirdly, Peace to Shabe. Peace, you have a question in the chat, but you can bring it out. Then I will invite Dr. Gideon to respond, and then other one senior members to those, and then we close. Other issues, we can arrange more other sessions for them. Thank you, and welcome. Dorcas first, Sylvia, Teresa again. Okay. Dorcas, are you online?
Yes, please.
Please
Thank
ask,
you,
and
Chair.
Dr. Gideon, you can note the questions, you respond to them, and then we close.
Thank you, Chair, for inviting me. I have a few questions, but maybe I would only need a little clarity. The presenter highlighted about the issue of multicollinearity, and this has been more elucidated by Professor Laura. However, I still have some questions. When we looked at the analysis run by Dr. Nkurunziza, we saw that the shopping price and the delivery time were positive and highly significant. Now, from what we know in literature, for example, Field 29, 2013, and 2018, they will tell you that multicollinearity exists when there is a strong association between two or more predictors. Those are the IVs. In this case, from the presenter, it was between the IV and the DV, that is the high collinearity. What would be his take on that, despite the fact that Professor Laura has also told us that it could result to issues such as having misvalues and outliers. My concern is, in a situation where I have high correlations between the IV and the DV, what would be the take on that? Secondly, why we also have the unstandardized and the standardized beta coefficients, focus by Dr. Nkurunziza has been put on the unstandardized beta coefficients and not the beta coefficients. Kindly throw more light on this, Dr. Nkurunziza. My third question relates to regression. somewhere when we're running the regression, we saw that you talked about the Durbin-Watson test, and that is where my interest was. And you said that this is only run where we are having longitudinal studies. However, I have seen so many studies, current studies, researchers that have run the test even in correlation studies. And yet we know that this Durbin-Watson test helps us to test for absence of serial correlations between errors. Dr. Nkurunziza, kindly, what would be your take if this is not tested in correlational studies that probably most of them are undertaking? And then maybe lastly, may I please know the acceptance threshold, acceptable threshold of the F statistic, even when the model is significant? I believe there is that acceptable threshold. Thank you very much.
Okay, Dr. Gideon, can you first respond to Dorcas? I think her questions are many. And then we go to Sylvia and Teresa later.
Oh, excuse me. Yeah, thank you for the comments. I think let me not go in the order since I have already seen other comments from the chat. Karen's was saying that can you see CSV directly to export the data to SPSS. My comment is that this one is not an issue. That one applies especially with smart PRS, but with the SPSS you can just export by choosing the Excel file. You don't need to convert the data. The F-change statistic. One, the reason why we rely on the significant levels, this is because the absolute values may keep varying, but what matters that even what you think is small may allow actually the values to be significant. I think Professor Ntai mentioned on that. I think what is important is that the significant levels depend again on the sample size. So it may look to be a small value, but again, when it is very significant. First of all, if you want to go into it, into the detail now, you know, to some people 0.3 sound to be small, others 0.1 sound to be small, but that one depends on the sample size. The other one is this question. I think it's a comment, either question or comment by Teresa on whether it's looking at R within and the R between. Actually, there's a third one. Which looks at overall. The R within, when you're looking at R within, you are concerned with the squared values, of course, from the mean, deviated, of course, from the regression. But basically, relying on transformed data, if you have your ordinary least square and then you use the transformed data, then you can get that R, which we call R within. But R between, again, this one, it comes in when somebody says, can you look at the fixed effects? And when you compute first and you look at the fitted values using the fixed effects, definitely the R you get again, that interpretation goes around that way. I think All of these coming from where you are coming from. For those use other programming software, more especially those fixed effects, you can't dodge them. The other one is, I think, also a comment or a question, which I saw from Mr. Sexivo, where I said the choice between hierarchical regression and multiple regression. Ideally, when you look at those assumptions that we consider apply to both, but what matters is what objective are you answering? You know, multiple regression cannot, you can't use multiple regression to look at the contribution of each of the variables. So if you have one of the objective that perhaps required you to look at what each predictor explains in the dependent variable, definitely you need to do hierarchical regression. The other one I think is Docus about the multicollinearity. Yeah, indeed, I know from the scholarly perspective, you know, as a researcher, you need also to take a position. You know, when you are looking at multicollinearity again, in simple terms, you are looking at whether those independent variables are highly correlated. If they are highly correlated, that could be very dangerous. They are highly correlated, yet they are all predictors predicting the criterion variable. So ideally, that would be something you need to pay attention to. And then I think, of course, you need to know what is the cause of that. What is the cause of that? Is your conceptualization fine or not? This is why, when I mentioned this, I need really to be conscious about where you are coming from. If you are coming from physics and you know that the physics are things which you talk about and you cannot really, if it is length, you know how to measure length. We are not talking about these variables which require the latent variables, you know, where if you come from psychometrician kind of perspective, if you are coming with that lens, definitely, and others coming from physics, there are things which you can find, the measurement you can't question. This is the instrument, it's well known. So what you get as high, it's not doubtable. So I think it also depends from where you are coming from. But if you come from pure science, you know most of the variables. Sometimes conceptualization has serious debate. And that's why validity and reliability is really one of the key aspects that you pay attention to. But sincerely, if you are looking at those quantities, the scalar quantities, which are well known, which have been proven, the measures have been proven, and you get high correlation, why doubt then? I think you need to know where you're coming from. On the standardized, I told you that when you go standardized again, you go to deviations. When you're interpreting, you are no longer in absolute values now. You are in standard, you're looking at it in terms of standard deviation. I think that's a conscious element you need to pay attention to. Don't interpret it as if you're looking at unit changes. First of all, those are standardized values. If you want to go into theory, then we can look at it from the Z statistic, how you get the X bar. I mean, when you look at X bar minus mu over sigma, over the square root of n, then when you standardize that way and you look at those those standardized values, you correct them, then you know interpretation cannot be the same as the other one. Ideally, the time may not be enough for us to explore all these. I think the rest, Chair, we can still discuss even after this presentation for whoever has a comment, one-on-one, since time is not our best ally.
Okay, thank you
Chair,
very much.
Chair, can I add in some? Chair, I wanted to add something to what
Okay,
Gideon
Professor.
has said, responding to the issues raised by Kalembe. One is relates to multicollinearity. Yes, it is true. Multicollinearity can be a very big issue in research. But I just want to encourage her to look at two things here. What we call the types of or kinds of multicollinearity, right? The first one is what we call structural multicollinearity, and this is very common when you are dealing with the time series data. If you create a model term using other terms within the same data set, for example, you have your X, right? But you square X, right? Then you create that problem of structural multicollinearity. And this is very common in econometric models where you bring in, and you need to really test for some of these things so that you detect. The other one is what we call data multicollinearity, right? And this is the type of multicollinearity that is present in the data set itself, rather than being an artifact of the model, right? And this is also very common. So I'll not really go into details, but yes, it is true, two variables might be related, but look at the VIF, the variance inflation factor. And when I looked at Gideon's VIFs, they were all below 2, about 1.1 something, 1 point something. That means there was no significant issue or multicollinearity in his data set. So sometimes you have those relationships existing, and they are true kind of relationships. The second one is an issue of F statistics that she raised. I remember Bernard Wabukala did talk about this about 2 weeks ago, I think, if I'm not mistaken. Just to remind you what he said, and again to refresh ourselves on what F statistics is all about. The F the F test, usually if you're going to have the F test, right? Now this F figure, right, is the test of overall significance, right, of the model. And it indicates whether your linear regression model provides a better fit for the data than a model that contains no independent variables. And you need to be mindful about this, because if you're not mindful about that, you just look at the F figures anyhow. And so in our case, what we need to do is to look at the F and see how the F fits in with the other regression statistics, such as the R squared, right? Because the R squared tells you how well your model fits the data, and the F test is related to it, certainly. So it's the overall model that you are talking about here, and that's why you know when you run the regression, it will give you model summary. Then you have the one with the F below. Then you have the other one with the beta coefficients, right? I know some people don't look at all these statistical outputs as related. So therefore, the F test will give you that kind of fit for the model. However, remember two things: that whenever you undertake to have any statistical estimation, you have hypotheses that you are testing, right? So if you're going to use the F test, right, you have the null hypothesis and then you have the alternate hypothesis. So the null hypothesis will state, right, that the model with no independent variables fits the data as well as your model. Now, the alternative hypothesis will state that your model fits the data better than the intercept-only model. So always interpret this in relation to that. Over to you, Ahmed.
Thank you very much, Professor. I think in the interest of time, Professor already proposed that we can get some time and discuss more issues on bootstrapping. I think given that majority of our participants and majority of our students on the platform are non-statisticians, there is more time needed to look into these issues very, very well. So we shall arrange more time, answer all of the questions, or we can arrange a Q&A session based on the same area. I think we shall discuss with the prof and see how to handle these issues. Allow me at this moment invite one of our students who has been very active in supporting others on statistics, and he should be able to really wrap up this very well. And I think he will be part of the panel to discuss in the next session on these other issues. So allow me call Bernard Wabukala to, as a statistician and economist, to give us the closing remarks today and the closing prayer. Thank you, and thank you for being with us today.
Right. Thank you, Dr. Walugembe, for driving us this morning up to this time. I also want to thank everyone who has been with us for all these hours today. Special mention to our facilitator today, Dr. Gideon Nkurunziza, as well as all the professors who have provided the comments and the suggestions to some of the issues that have come up as we continue learning and sharing with each other. Today, I think it just reopens what we always do every day. At one stage in your manuscript or whatever, at least the issues we have talked about today will emerge. So I think this is a very good platform for us to continue doing this. Specifically, this section of correlation and analysis is what constitutes the social science research today, as we test theories and relationships here and there. So I think based on these discussions, I want to suggest that this is just a start of this particular topic. I don't think it will ever end because we keep getting new methodologies and options. Today, there was a mention about outliers. What do we do with them if you have them? There are outliers out of errors, which you can check by running descriptives, and therefore you can isolate them and drop them if you know they are actually errors. But there are some outliers which are real information or factual or facts which you cannot drop, because by dropping them, you are losing actually very important information. So for regression, for instance, there are now new approaches of handling regressions when your data set has outliers that you cannot drop because they are actually part of the important information you have collected. Maybe we'll have some session on that as well. Two, I like the clarity Professor Antai has mentioned on multicollinearity, those two angles, where you have two variables, X and Y, very different variables, but they appear as if they are doing the same job in your regression. That is, which is structural multicollinearity, as you called it. But there is also collinearity arising from the data set, like he put it. You have a variable called maybe gender, male and female, and we have ones all through. Then you have another variable called unemployment status, and you also have ones. So the variables are different, but the data is making them look like they are the same. So again, how do you handle such an issue when it is from the data rather than from the structure of the variables themselves? And those, I think, issues, Chair, for me that maybe we should now start enlisting and tackle them going forward. With that, Chair, and thank you for the permission, I would like to call everyone, and we say short prayer as we close the day and go and do other things. Let's pray. Thank you, God, for this day, for bringing us close together again this Sunday morning, for the wisdom, for the thoughts and the discussion that we have received on this platform. We hope that this knowledge goes and builds our works, our contributions to society and knowledge. And we pray through you that in the events to come, you'll keep us enriched with more ideas and suggestions for the greater good of this platform and our region at large. In the name of Jesus Christ, I pray. Amen.
Amen. Thank you very much, Bernard.
Amen.
And thank you, the presenters, Dr. Gideon, the professors. Thank you for the support. Members, we meet next weekend, God willing. Thank you. And have a wonderful weekend.
Nice weekend.
Nice weekend to you, Professor.